Hello, class. This is GT501. Welcome back. So I think we finished our lecture material somewhere here, page 20 and then 21. So we'll continue from there, okay? Let me finish lecture 1 first and then move on to lecture 2 and 3. So I'm going to provide you with lecture 2 and 3 today and tomorrow. And then you're going to have to watch those videos before we meet on Tuesday, 3 p.m. Okay, so let's get started. So here, the point was people were putting a lot of various efforts and developing various technologies for fuel economy improvements, and these are just a few of those. And one of the major factor is the weight of the vehicle, obviously, but maybe it's not clear, the clear relationship between weight and the fuel economy. And this slide shows a quick relationship between those two using some basic equations. So this equation here shows energies provided by fuel equals mv squared over 2 eta fc. And where is this coming from? Well, let's start with this equation here. Fuel energy equals to fuel mass times QLHV, low heating value. If you have taken thermodynamics, you're probably familiar with this. But anyway, this low heating value converts mass into energy. How much energy for a given fuel mass? So that converts into energy from the fuel. And fuel economy, by definition, is distance divided by fuel volume. And if you plug in variables into these values, distance and fuel amount, then this is what you get. And what this means is that fuel economy is proportional to efficiency divided by mass. And here the point was fuel economy is inversely proportional to mass. And these are real data. That was quick math to show the relationship between efficiency and fuel economy and mass. And this is a real number, real vehicle fuel economy data. This is a bit old, but the relationship is still valid. So x-axis being weight and y-axis being fuel economy. And you can see that those two variables are inversely related. And we want to find out how fuel is consumed and where these energies are, lost when it comes to fuel economy. So this figure shows a quick summary of that. So let's take a look. So when you put fuel into engine, by the way, this is conventional, internal combustion engine powertrain. In this case, when you put 100% fuel input to the engine, there will be 62.3% of losses from engine losses from converting this chemical energy into mechanical energy. So, and that's just not that, but you also lose 17% during standby and idle. And what you actually get from the driveline or input to the transmission is 18.2%. And that, by the way, there's also accessories of 2.2%. Okay, like lightings and pumps and those things require energy too, and usually those are coupled to powertrain. So this is it. 18.2% out of 100 is going into your drive line, your wheel. Among that, you also lose 5.6% of driveline losses. There's transmission. When you transmit this power, mechanical power, to the wheel, you also lose energy. Depending on the vehicle, this number may vary, but you will have to lose some energy there. By the way, people are trying to improve engine losses, so reduce that. And standby idle, so we have engine stop-start technology, and then reduce accessory losses and driveline losses. So people are doing all kinds of things to reduce these losses, okay, to improve fuel economy. And then finally, how much the amount of power and energy you provide to the wheel is actually only 12.6%. That's how much you actually need to move the vehicle. And you're putting 100 to get that 13%. Okay, so you can see where this low efficiency coming from. Okay, and if you look at how this 12.6% energy is used or consumed, there is aerodynamic drag. We can avoid that. There's rolling resistance from tires and everything. And then there's inertia. When we say inertia, we need to put energy into the wheel and vehicle to accelerate the vehicle. But if you think about it, accelerating a vehicle doesn't mean losses. It doesn't. You're not losing energy. It's just that you're converting, mechanical power or torque into kinetic energy. Okay, so when you actually the time you're actually losing this kinetic energy is when you're braking, and that's because of the inertia. Okay, And when you're braking, if you use just friction brake, then you're losing all of this. Okay, so people have been thinking, how can we remove or reduce these losses? People have been doing a lot of aerodynamic study to reduce this number, and same goes with rolling resistance. Less parts, less moving parts, smoother bearings and lubricants, and tires with lower rolling resistance, and there's inertia, lower inertia, so lower braking energy. And then there is one more thing. With electrification, we can reduce or recuperate this braking energy and then use it later. And people have been also trying to improve driveline losses using more efficient transmission, more efficient torque converter, and so forth. And then better engines to reduce engine losses, trying to remove standby idle condition, because at that time engine is running, but you're not going anywhere. So efficiency is 0. So you want to reduce all of this, a little here, a little bit there, a little bit there. So that's what people have been doing. And with electrification, you can improve a lot of these losses, reduce these losses. You can improve engine losses, you can improve, idling problem, you can reduce braking, and so forth. So, and here is one question. And I'd like to hear some answers during discussion session. How much energy, how much fuel economy will be improved if you improve 10% of, say, rolling resistance. Let's say you reduced 10% of rolling resistance. Okay. Or you could also improve 10% of driveline losses. Okay. How does that relate to actual fuel economy, which is the fuel input to the system? So which one do you think has a bigger impact on the fuel economy? Okay, let's talk about it on Tuesday. Okay. And let's stop here for lecture 1. So that concludes lecture 1, and then let's move on to lecture 2. Okay.